Massive thank you to Matt and John for having me on. Admit, someone else is joining. Massive thank you to Matt and John for having me on at Leeds Sharp. I think I originally did a talk at Leeds Sharp like 5 or maybe 6 years ago, like a long time ago. I think it was in call credits offices maybe, and it was like there was some F Sharp talks or something like that. It was a long time ago. So it's, yeah, half a decade has gone on. My hair has grown quite substantially because I'm not able to have a haircut at the moment. So apologies. Today I am going to be talking about IoT. That's what we do. So I guess as a bit of an introduction about me, my name is Jordan Appleson. I'm the Chief Executive Officer of Hark. You can find me online on Twitter. Jordan is on fire. That's actually a band reference. I'm a massive Alexis on Fire fan, for those of you who know the band. And I never really got rid of the handle from being a 15-year-old, so I guess it's kind of stuck. Email is my name at harksys.com. And my background essentially is kind of been building distributed systems with my friends for kind of the last, I don't know, several years. So that's like high throughput data applications where it's processing information and analyzing data and then spit it out for kind of people to use, and hopefully it'll be useful. I mean, that's kind of the point of why we're all software engineers, I guess. In terms of an agenda for today, I'm going to talk about basically a little bit about Hark, what we do, a bit about our technology stack. The conversation today is all about kind of IoT on the edge, and in the cloud, and what that looks like. And when I talk about scale, I'm talking about at the scales of kind of tens of thousands of devices or sensors for kind of a single deployment. What that looks like across like a UK deployment in terms of like lots of gateways, lots of these IoT devices in buildings, and kind of a few key challenges I guess we faced by doing it. So some of it's technical, some of it's not, some of it's kind of obviously the edge in practice is going to have lots of photos of what it actually looks like on the edge. As a software engineer, you know, we all write code, but like, what does it actually look like physically when you get into like these industrial systems? And then I'm going to talk about a little bit about the cloud. Now, there's a couple of the Hark team on today, so if I get anything wrong, I fully expect some of our team to correct me on some of the challenges. They'll be like, nah, that was easy. Like, we've totally solved that. But so yeah. One thing to note, I guess, as well is, you know, when it comes to the technology in the cloud, like there's lots of different ways of doing things, lots of different ways of solving problems. I mean, this is just kind of how we've solved it, or tried to solve it anyway. So after kind of I've gone through this, we'll have kind of 15 minutes for questions. So yeah, feel free to like grab a gin, as I think Simon has, and we'll go from there. So Hark are a technology company. We started in 2016. Ultimately, our mission is to improve efficiency, maximize yield, and reduce waste. And what that means essentially is that we're mainly an energy technology or building automation type company. So we're looking at improving efficiency around energy, kind of downtime reduction, kind of automatic and reducing waste energy, that kind of thing is where we kind of were born out of. We actually started off in life sciences, where we manufactured our own hardware when we were trying to monitor temperature for kind of cryogenic systems. That's where we started off in 2016. So everything that we do now has been born out of actually building and shipping our own hardware, like IoT hardware, to connect stuff to the cloud. Although we don't do that anymore because I suppose you know, building hardware is hard for various different reasons. I actually did a talk on that not too long ago, but it's probably a story for another time. Ultimately as well, like our technology is used across lots of different industries. So right now we're shipping our technology to kind of retail and supermarkets, facilities management companies, industrial manufacturing. I've talked about pharmaceutical and life sciences. And, you know, we're working a lot with kind of renewable energy as well at the moment. So like energy storage systems, controlling buildings based on energy prices, that kind of thing. So the Hark technology platform is essentially like a cloud-based platform that allows you to connect assets, building management systems, energy meters, you know, industrial process controllers, that kind of thing, to the cloud, and stream all the sensor data out of it in real time, where we analyze it for all sorts of different things, whether it's downtime reduction, energy management, and more recently, the last kind of year and a half, we've been automatically controlling buildings based on the output of our platform. I'm going to touch on a little bit of that today, but yeah. So in terms of what we do, like monitoring wise, 80% of what we do is typically energy and power monitoring. And like, that's not necessarily like your half hourly metering data that you may have come across for your home energy. I'm talking about minute by minute instantaneous power values, frequency of the grid, how much you're consuming on a minute by minute basis. We've got oxygen, CO2 sensors, temperature, humidity hooked up in like big labs for life sciences companies. And they're monitoring like, you know, how much gas is in my lab, because if there's too much nitrogen or too much argon or whatever and it's displaced, then someone needs to know, because it might kill someone, I suppose. But that's kind of the end spectrum, I suppose. The three kind of use cases we kind of focus on are energy management now, facilities and asset health management, and kind of industrial maintenance. So connecting to all these assets and effectively monitoring them and controlling them to increase efficiency, you know, alert people to when things go wrong. How we do that as a business is kind of this kind of edge technology, right? So the edge, you know, IoT, buzzword galore, right? But it's actually quite straightforward, right? We have some software that runs on an industrial gateway. It could be a Raspberry Pi for all we care, although typically industrial customers don't want to stick a Raspberry Pi on their really expensive piece of equipment. So we'll use kind of an industrial gateway. Essentially, our software stack that runs on that edge allows us to connect to different devices downstream. So that might be heating systems, energy meters, process automation controllers from any brand, like whether it's Schneider Electric, Honeywell, Siemens. And the way we do this essentially is using industrial protocols that have existed for tens of years, many years, from even some from the 80s, which are horrific for a software engineer that is, you know, a lot of us are probably used to like JSON APIs, you know, GraphQL is the new thing, all sexy stuff. I'm telling you now that the industrial IoT world is not sexy when you're on the ground, and that's kind of what I'm going to prove today. It sounds really good. It is really fun. It is dirty. It is really dirty. Like, I mean, physically, like you get your hands really dirty on oil and all sorts of stuff. So our edge software runs on a gateway. It communicates with the cloud. What our edge software is doing is communication translation, like translating those old protocols into, you know, the stuff we like, you know, MQTT, AMQP, you know, HTTP, get it up to the cloud and go back downstream with control signals. And the reason why we're doing this is because, well, no one really wants to replace devices with new sensors, right? And I'm going to touch on that today. Like, there are sensors that already exist in these systems. A lot of IoT is all about, yeah, put more sensors in, we'll retrofit. And a lot of businesses are like, well, that's kind of expensive. We've already kind of got the sensors. We just want to get the data out of them. So in terms of us as a business, energy management, where we're basically looking at utilization of energy, trends, spotting anomalies, performance monitoring of assets, that kind of thing, and then actually controlling buildings based on rules and digital twins and all the buzzwords. So going to touch on actually what we do, a couple of customers that we work with, and then I'm going to dive right into, well, like a bit about kind of device connectivity. So
Jordan, can you just check, sorry to interrupt, can you just check if there's anyone in the waiting room?
I cannot see, hold on. Can I just make you a, just make me
event host also.
Yeah.
I think that's easy.
How do I do this? Oh my goodness. Make host, there you go. There you go.
Thank you.
While we're interrupting, can I just mention, if anyone's got questions during the talk, they can just put them in the chat, and then Jordan will have a nice list of things to go through at the end.
Yeah, absolutely. And you can probably see my, yeah, okay. I think I've sorted all that out. Great. So where was I? Deployments. So we work with 2 of the top 4 supermarkets in the UK. This is one of them. They have a big orange logo. You might have heard of them. And essentially what we do for them is monitor their assets, their energy from their assets in real time, as well as control buildings. So we're in over 600 stores. We're monitoring over 24,000 assets. We're doing about 200 million readings a day through our platform, which is then kind of, I've not lost internet, have I? Can everyone hear me still?
Yeah, you're okay, Jordan.
Okay, sorry, my computer popped up with a network notification. That's fine. Yeah, so we're monitoring individual assets from bakery ovens, refrigeration systems, lighting, solar arrays, and crunching all those numbers to give reports, real-time reports on energy anomalies, like spotting anomalies with assets around how much energy they're using, and even controlling the buildings based on energy prices. And to give you an idea of what that looks like is, the prices of energy, they change through the day for a lot of commercial customers, especially big customers who spend a lot on energy. So, you know, you've got a red period, an amber period, and a green period, which essentially the price changes quite substantially. For a supermarket, that's quite important. And they have a period during kind of the winter time where, you know, the price can spike by kind of 1,000-fold on average, technically speaking. And what our system can do is when it receives a warning about kind of effectively a price spike, our system will orchestrate changes across buildings in real time within 60 seconds, reduce how much power it's using, as well as, you know, allow the business to schedule different logic to happen on the edge, control lights, look at things like occupancy, turn things off, and, you know, a whole host of other things. In terms of the life sciences stuff where we started, you know, we're monitoring you know, lots of locations with lots of sensors, temperature, humidity, oxygen. That's mainly for regulatory compliance. You know, it's quite interesting. We're in this kind of COVID lockdown scenario. A lot of these vaccines, when they come into the country, when they're kind of manufactured, they'll have to be stored in stability chambers about 5 degrees centigrade, and they can't really move back and forth. You know, the temperature isn't really allowed to move, because if the vaccines denature, they'll become kind of, well, useless. So where we started off was actually monitoring lots of temperature systems to be able to kind of alert people to things being broken and that kind of stuff. And lastly, this is quite an interesting one, which I'm going to talk a little bit about, is controlling energy storage systems. So this is a 240 kVA battery, Tesla battery in Manchester. Our system is basically monitoring it and controlling it based on, you know, different, you know, periods of energy prices, as well as, you know, even it's used to trade out. So you can buy energy when it's cheap and sell it when it's more expensive, which is quite an interesting, quite an interesting like thing. I mean, we're mainly the control aspect of this, but yeah. So let's talk about our technology stack, get that out of the way, and then you can, you know, what are we using to build specific things. So we're predominantly a C#.NET house in terms of our backend systems. So our backend systems predominantly are written in .NET, like .NET Core, running on Linux containers. We're very heavily invested in TypeScript, and we've got quite a few of my engineers on my team are here today who typically write in TypeScript every day. Obviously, when it comes to the front end, we've got React in there. We do have Go in our stack in different periods. We actually have Go running on the edge, so we compile programs to do protocol translation that are containerized in Go, because it's small, lightweight, and fast for doing a lot of stuff. In terms of data layer and event processing, that's, you know, typically column-based storage engines for time series data. I've done talks on this before, and again, stories for, you know, war stories for another time maybe. But it's typically kind of Postgres, SQL, you know, Cassandra we've got in play, Redis. We've got quite a bit running on Cosmos DB on Microsoft's cloud stack, which was in it again, war stories for that for another time. And then in terms of event processing, we've got you know, a lot of our systems are based on events. So event hubs, so like Apache Kafka for distributed commit logs, as well as RabbitMQ for, you know, effective message brokering. Cloud infrastructure, it's all Microsoft Azure, and we are pretty much a Kubernetes shop now. We had stuff running in web apps. We're still migrating a few bits over from legacy systems, but ultimately, you know, the idea around kind of what we do with our infrastructure is if we can run it on Kubernetes, we can pretty much run it anywhere we want. On the edge, it is Docker. It's Docker on the edge, and we use a variant of Ubuntu called Ubuntu Core, where we can ideally serve a hardened server layer if possible for certain devices, but it can depend. We're kind of agnostic to that when we're dealing with massive enterprise deployments, but typically, you know, containerizing things on the edge is kind of a thing that we've been doing for the last kind of 2 or 3 years. It works really well when it works, I suppose. And in terms of the data science stack that we use, that's, you know, your typical data science stack. So we have Python. A lot of our, you know, team use Jupyter notebooks to explore data, test out algorithms. We've got Pandas, scikit-learn, and yeah, we use a bit of TensorFlow as well. But, you know, this is pretty much the stack that runs it, runs our platform. So let's talk about the edge. Now, this gentleman is the edge from U2, so I've been told. Yes. When people talk about the edge, there's kind of like buzzword, because it's a buzzword now. People assume it means different things. Like some software engineers, rightly so, will assume that it's kind of edge compute. Industrial companies might say it's industrial gateways. Businesses who are dealing with digital twins will say, well, digital twins and the edge and containers. And that is true. That is kind of IoT, star, existing things rebranded that now constitute the buzzword of IoT these days. Now, if you're talking about downstream devices, which is where we live in the real world, when you're trying to physically connect to assets, we're talking about energy systems, meters, industrial assets, sensors, building management systems, anything that is physical that you want to connect to that has sensors in it. That's what we class as kind of edge devices as well. All of this together is, the edge umbrella. I am basically going to take you through a tour of these downstream devices and what this looks like in the field. So you're probably thinking, like, what is this asset that you speak of, Jordan? What is the edge devices that you speak of? Well, when we're talking about industrial assets, we're talking about things like compressors, fridge plant. You walk into a supermarket store and they've got all these fridges keeping everything cool. Funnily enough, you've also got the building trying to keep everyone warm as well, which is kind of a paradox, an oxymoron, a juxtaposition, whatever you want to call it. But ultimately, when we're talking about industrial assets, we're talking about heavy machinery, furnaces, that are making bottles, glass bottles, stability chambers in life sciences, and there's a whole host of other things. We've been in some very ridiculous rooms with very ridiculous equipment in that I wasn't allowed to take photos of, but fortunately, we've been doing this long enough that I can show you some photos. Now, what's really interesting about these industrial assets is, they are all what you would class as a PLC, a programmable logic controller, right? They are used for manufacturing, automated tasks, industrial systems, that kind of thing. They're typically programmed by they're not necessarily software engineers, they're PLC engineers, and they use block diagrams, block functional logic, even some code to be able to run these systems. And the reason why that is the case is because usually these are running real-time systems. You can't run a virtual machine or, on an operating system that, when I say virtual machine, I mean virtual runtime, where you can't guarantee time, for instance. And that's why real-time operating systems are really important. There are industrial standards around this. You can't get away from them. You're not going to be replacing an industrial system with a Raspberry Pi when it's safety critical. It's just not going to happen. So what's really interesting about this is they are connected to sensors. If you go into a building, if you go into a supermarket store, if you go into any building, there is a thermostat and a building management system, and that is connected to sensors, in order to control the temperature of a room, right? But interestingly enough, all the fridge plant, all the plant that's powering that has its own sensors as well, which you can use for, lots of different interesting kind of like performance analysis. So our job is to establish connectivity to the existing sensors, because ultimately, you don't want to go into a customer that already has, in our case, loads of sensors and go, we will add 50 more sensors and it will cost you X amount of money. So our job as a technology business is to use what exists. And I'm going to show you a little bit about that now. So if you come into our office, you'll see lots of stuff that looks like this. This is a demo kit that we have in our office that we use for testing for different things. The PLCs come in all different shapes and sizes by all different brands. So on the top left here, we've got a little PLC controller that essentially its job is to control furnaces or process control systems. It takes in analog signals from temperature and turns things off and on based on logic that runs on it. This black box is an industrial gateway. This orange thing here, keep an eye on that because that might pop up again in another photo, is a building management system manufactured by Honeywell and Trent. They already exist. These things are 20 years old. They've been running. They're there. No one wants to replace them. They work just fine. On this middle layer, we have energy submeters. So meters that are like effectively monitoring energy, kind of like what you've got in your home, but with a lot more kind of, it's got a lot more to it. So you can not just monitor consumption, you can monitor harmonic distortion of energy, you can monitor phase information, all sorts of stuff. You'll typically see these in industrial outfits where they're really heavily used to actually track performance and energy on a kind of a commercial industrial scale. On the right hand side, again, more PLCs, just different use cases, same stuff. What's really interesting is this is literally the same thing as this, that they're all take something in, turn something on and off, right? Usually an electrical load. That electrical load downstream is usually a fan, a compressor, no different to your boiler at home where, oh no, it's under 20 degrees, let's turn on the heating. Or if you're my dad, you'll never have the thermostat on more than 5 degrees, which as a kid, I can tell you, I almost froze to death as a kid. But they're all analog systems, not necessarily digital. Anywho, below here we've got an industrial black plane, which is basically got a vibration sensor hooked up to it. That's this thing. Interesting fact, one of our principal software engineer, Alex McNair, wrote a game for the office where you had to, we had 3 lights, a red light, a blue light, and a green light. And you had to walk with the vibration sensor in your hand across the office without making the vibration sensor turn the light red. That was a really fun game. One day when we're all out of lockdown, we can play this game. We can like have a Hark party and play it. Now, this is something that's like, this is all on our desk, right? This is all on the desk. This is not what it looks like in the field. What it looks like in the field is this. This is another PLC controller that does lots of things, right? This is actually a Mitsubishi PLC controller. It speaks some languages. There are a lot of wires there. And what those wires are electrical loads to turn things off and on. For instance, a motor to move something forward or back on a production line, temperature sensors, I don't know, heaters, could be anything. Lots of wires. I'm going to tell you now, none of that is TCP/IP, right? It is electrical signals, voltages, things that you don't want to touch accidentally or plug into your computer. Again, it's all to do with power and turning things off and on. So what we have to do is go in and find a way of connecting to this, also without without impacting any service, right? That's kind of the important bit. So what else do things look like? Let's have a look at, so what that was actually is a production line for basically packaging things. This here on the left-hand side is a HVAC drive. So a HVAC drive, essentially, you've got big fan systems. If you go onto the roof of a commercial building, you've got these massive fans spinning. Well, you can't just plug that in. You have to be able to regulate the speed of that. There's a whole industry worth of drives that are, and you have to connect to them and control them and all sorts of things. On the right-hand side, we've got a CHP machine. A CHP, if anyone's aware of that, is combined heat and power. So what this is a unit that can generate electricity and heat. So it's like a boiler at home, but can also generate electricity. The idea is if you combine them into one, it's more efficient because, your heating system essentially is generating heat. So let's turn that into energy as well, into actual electricity. So you'll see a lot of these in the renewable space now. Well, I say renewable space, the efficient green energy kind of thing. And again, sensors. You can see actually on this ProFace screen that you've got, engine water temperature, water in temperature. So you've got a delta between water in and water out, which is actually a really important metric when you're dealing with heating systems, because the higher the delta, the more efficient it's running. The lower the delta, why is it even on, kind of thing. So really interesting stuff there. All looks quite clean right now, right? What's interesting to note, right, is that we just looked at a HVAC system, a refrigeration system, ovens, energy storage system. They're all basically PLCs, right? They're just shaped differently. They just communicate differently, but they're all some kind of logic controller that has been programmed. Now, it starts to get a bit messy, right? So again, notice anything you've seen before. This is an actual deployment or an actual box in the wall where you see a high voltage panel that says, 450 volts or 415 volts behind it. This is typically what's behind it. Lots of electrical relays, some control systems, some network switches that are probably bolted onto the wall somehow that, from 20 years ago when someone's tried to get remote access. It's all a bit, undocumented, should we say. On the right-hand side, we've got control systems, and industrial gateways, and it's just wires of electrical stuff going in and out, and that's what we have to connect to. We need to figure it out. A couple more. This handsome young fella is Bradley, one of our engineers. He might actually be on the phone today, so give us a wave, Bradley. What is stood behind him is a solar array, 200 kilowatt solar array that is on a big building. And again, same type of technology, but this is what a solar array looks like. Again, it's that the inverters themselves, again, they're kind of logic controllers. When it's bright, please invert the power from DC to AC and feed it into the grid. Interestingly enough, they blow up, believe it or not. Inverters have a tendency to set on fire. So monitoring them so they don't set on fire, or they've set on fire, is kind of really important, especially if you've got hundreds of these across the UK and they're on top of buildings that you don't want to burn down. So, good use case. This is where it gets a bit dirty in terms of like the kind of things. I say dirty, it's not. This is a glass furnace. Really, really cool stuff. You've got molten glass, PLC controller controlling that. Lots of cool stuff. Very hot, 1600 degrees. Very, very hot. Don't want to put a Raspberry Pi anywhere near that. I'm telling you that now. So, how do we actually connect to them? right? That's kind of the key thing, right? So as we've kind of just established, you know, you don't just simply go plug in to whatever you find in the panel. And as much as I've tried that, and we've tried that, and we've gone through the pain of trying to do that, things tend to blow up, literally blow up. I mean, we've had things blow up, but in a controlled way. Let's just talk a little bit about interfaces. So everyone, I would hope, is familiar with serial comms. Maybe not, I don't know. It was an interesting one, but ultimately a lot of these systems are designed to communicate over, like, from, you know, they're old, you know, they're old because they work and they've got a lifespan of 30 years or 15 years. So, you know, that's what these businesses, if they don't buy something they're going to replace, like an iPhone every 2 years, because you want the latest operating system and the latest connectivity, they just want their building to bloody work, and for as long as possible, and for as minimal amount of cash as you can imagine, because that's going to be cost effective. So serial is still very much in play. It's been in play for many years, and typically it's a 2 or 3 wire bus, which you can actually daisy chain devices to. It's got, you know, effectively a data A, a data B, a plus or minus, and all that is essentially voltages going up and down, creating binary zeros and ones, right, essentially. And it's really interesting that, you know, you can actually daisy chain these devices with less wire, less cabling than Ethernet, you know, Ethernet cables, right? For every device you'd want, you need an Ethernet cable. That's a lot more wire. With these, you can actually daisy chain them together. So actually, it's more economical these days than even Ethernet is. So why would you not want to use it? It also has a potential theoretical range of basically 1.4 kilometers on a chain, which Ethernet can basically do 100 meters without kind of a switch or something to kind of boost the signal. So there are some downsides to this. If things are daisy chained, only one device can talk at once, right? And a lot of legacy devices will be in this configuration. So that kind of limits you in terms of how much data you can pull over the bus at any one time. If you've got 40 devices and that each device has 40 sensors or 100 sensors, and you want to get through, you know, all 4,000 sensors in the space of a second, it's not going to happen, right? And we have to be mindful of this, because realistically, you know, you might not need data every second. You might need data every second, who knows? It's just important to note that when you're connecting to these systems, you can't just plug it in and be like, right, let's just bloody let's DDoS the machine that has been stood for 20 years. You don't really want to do that. Now, this is an interface, right? You know, I remember having a computer when I was a lot younger with you know, one of those serial ports in, right? It's the same stuff, apart from, you know, it's not a mouse connected to it, I guess. So that's the interface, but, you know, essentially the interface is just the ability to get zeros and ones over wires, right? So you need protocols on top of those interfaces, right? Interesting point about interfaces in general. Everyone, I'm sure, has seen these. You know, you've got DB9 connectors, you've got these Molex things, which are just absolute pain to wire in. This is the problem as well we've got with IoT these days, is you've got big manufacturers like, you know, software companies, server manufacturers, building IoT devices using connectors that they've used in the server world, thinking it's going to work in the real, you know, manufacturing world. I mean, we've seen some awful wiring things that, you know, in fact, funny story, we had to spend 3 hours wiring one of these Molex connectors because the crimping tool wouldn't work, because, I mean, it's just crazy. The other thing that's really interesting in this space as well is everyone's seen Ethernet cables. They know what an RJ45 looks like. They know what RJ11 looks like. So do businesses that have built industrial controllers that use those ports but don't put TCP/IP through them. They run voltages through them, like high voltage through them, which is really funny when you get a developer saying, oh, that's an Ethernet port. I'll see what IP address I got on this device when I plug it in, and your computer goes bang. That happens a lot, because effectively, when I say that happens a lot, people mistake these ports for things that they've seen in the real world in terms of computers, and they're not. We are working with systems where they have 60 volts running through an RJ45 line. Basically, it's a serial port. It's a serial port with voltage running through it to power downstream devices. You know, basically there was this, we had this thing once where someone tried to plug an Ethernet cable into it, plug it into the computer, and the computer just went poof. And we're like, well, that was silly, wasn't it? Not us, fortunately, but, you know, it's funny. It's funny to look back on. It's not at the time, because obviously, you know, a Surface Book is a very expensive device, and if you blow up a Surface Book, that's kind of $2 grand, right? Anyway, right, interfaces, TCP/IP. This box is intentionally left blank because I'm not going to go through TCP/IP stack on this call, but I am going to talk about the fact that you've got TCP and UDP, and actually you'll find that UDP is used a lot more for these industrial protocols than TCP, mainly for self-describing protocols as well, and I'll touch on that. So, protocols. We're going to talk about Modbus today, very briefly. Modbus serial. So, Modbus was designed kind of in the 80s as a way of connecting devices together. It's essentially runs on a serial line, and you request binary data over it. So you say, hey, this binary address, I'm expecting some data of this length, please give me it. And some binary data will come back on the protocol. And remember, only one device can essentially talk any one time on that bus, right? But it's very easy to work with, very easy to work with. Well, it's meant to be very easy to work with. Over the years, people have bastardized the protocol and done all sorts. Tesla have bastardized this protocol to the nth degree. I honestly can't believe what they've done with it, but fine. It's a very prominent protocol because it is easy to understand and work with, and we see it every day. Thousands of the devices that we connect to typically run Modbus. There is a TCP/IP version of it where it wraps the protocol, binary protocol, in basically frames and pushes along the TCP/IP network. We're not going to talk about that today, but that's one protocol. BACNet. This is a building management protocol. It's self-describing. So the key thing between Modbus and BACNet is that you need to know upfront what data you're asking for. So you need a manual, right? You need to know the address of the data. You also need to know what it is, because it's not going to tell you, hey, this is an integer or an enum. It's literally just going to give you 2 bytes, and you've got to figure out what the hell you're going to do with them. Like, how are you going to pass them? Is it big endian? Is it little endian? Is it least significant bit, most significant bit on the protocol? You're going to need to know all that to some extent. There are defaults, don't get me wrong, but like I said, people mess with this stuff to the nth degree. So when you're going to connect to things, I've got a funny story actually, which I'll talk about at the end, where we had to ring round different countries to figure out why a protocol wasn't working, because it's just ridiculous. I mean, funny story. I had to add on international bolt one to my O2 account to ring all these countries without getting a ridiculous bill. So good times. So BACNet, building management systems. You walk into big buildings, something is probably running BACNet. It's TCP. Well, it's a UDP protocol actually. And can use standard networking gear. It also runs over serial in different ways as well. So what you would do in case of this protocol is go and ask for data and say, hey, network, tell me what you've got on it, which sounds really good, right? Like, you don't need to know the manual. You'll just go, tell me what sensors you've got. It'll come back with some data and you'll pass it and you'll be like, oh, these sensors are available. Brilliant. Now, remember this was designed a long time ago, and building management systems, the Internet of Things wasn't really like a buzzword. So when people put configured systems that, building management systems, they didn't really care about this BACNet thing, to be honest, which means you have challenges with this. And I'm going to talk about 3 core challenges when it comes to this kind of stuff. 1, the PLC stands for programmable logic controller. So the P means programmable, which means software type engineers have programmed something on that thing. Because it's pre-programmed by a third party, no 2 devices are the same. That means figuring out what the device is doing, what things are where on the PLC, like what registers to query, is usually non-standard. In certain cases it is, in certain cases it's not. So this means it can be time consuming and a lot more challenging than just plugging your serial port in and going, yeah, give me the data. So that's the first challenge that we have to go through, day in and day out. We've kind of standardized ways of doing this, but it's a hard problem because you've got things in from 20 years ago that you probably don't even have a manual for anymore, and no idea what it's doing. It's like that old server in the data center that no one knows what it does, but when it goes down, the company goes down. And once it's dead, it ain't coming back. It's that kind of thing. Labels. Labels is a hilarious challenge, because when you query that building, going back to BACNet, and you say, hey, give me all the sensors on this network, and it tells you what the names are. Someone has actually programmed those names in, but they haven't, because they haven't thought about someone 5-10 years in the future figuring out what these names mean, because they've had a job to do. So you'll get sensors like ABDE1, and you'll be like, was this meant to be the alphabet? I don't know. What is it? Is it a temperature sensor? Is it energy? And you'll have to find a way of figuring that out. It's kind of like Modbus in that respect, because you don't know what the bytes mean. Well, even if you've got a number that says 21, what is that? 21 parrots, 21 energies, 21 temperatures? What is it? So this is a really key, like, important note when it comes to designing or retrofitting systems and figuring out what's already on the edge to connect to. And then you've got mass provisioning and deployment, which on it, you know, you can't just kind of connect something, test if it works, control F5, because if you wired it incorrectly and you've blown something up, you don't really get a second chance. And that's really important to know. So mass provisioning and deployment, you know, it's a team effort. Documentation is important. Standardizing on tools, automating things, really important. Testing is also very important. I know these are all obvious things, but they are significant challenges. You know, we ship thousands of gateways out just to one customer to do very similar things in every store, right? And, you know, we have a standardized configuration, but everything in the store might be different, and you've got to make sure you know how to basically tweak things. So that's the edge, right? That is the edge. I'm now going to talk about the cloud. There was no U2 member called the cloud, unfortunately, so I had to settle for this gift, which I think is very nice gift. So I'm going to talk about 3 or 4 architectural points in the cloud. I'm not going to spend as much time on the cloud as I have on the edge, because a lot of us are familiar with the cloud. So telemetry ingestion architecture. Just going to give you a high-level overview of building out systems to ingest large amounts of time series data. Talk about kind of event-driven architecture. So we use a lot of event streams to basically expand services to listen for what they need, and that's kind of an important point. You know, when you deploy things, you can't really take certain things down for long periods of time. And, you know, actually deploying new services, listening to events on a stream is way easier than having to figure out how to send API requests back and forth between different systems. Confirmation of synchronous state updates. So when you're dealing with devices connected via the internet, 4G, Wi-Fi, they will go off all the time, which means if you've got thousands of devices in the field, guaranteed, you know, hundreds of them can be offline for 10 minutes, 15 minutes. Not all of them will be online at any one time. That means that if you're pushing down updates to those devices, you can't be, there's no, it's non-deterministic as to whether or not it's going to come back and say, yeah, I was okay, this is good. So keeping that simple is really important. It's a challenge, even when you've got it right, because, you know, your device might go off for 4 weeks, and then there's other things, which leads me on to the conversation around if you've got a device that's ingesting a lot of data on the edge, you send it to the cloud and it goes off for, say, 6 months, and it comes back, it will fire off all that data it's collected as fast as it can. And that can basically, not, you know, one device isn't a problem. What happens if you have an outage for a customer who's got thousands of devices, and, you know, you've got, call it 40 gigabytes of data coming through in the space of a minute, which doesn't sound like a lot, but it kind of is when you've got infrastructure that's just used to a standard load. So high-level architecture, I'm not going to bore you with this diagram. Microsoft put it together for us because they were like, you must have an Azure architecture diagram to reference the architecture in Azure. And the way our system is set up is kind of into these, I don't know, 1, 2, 3, 4, 5 sections. System connections, what we've talked about, so the industrial edge, the compute edge, where you're doing things like the software side. Then you've got our cloud services for telemetry ingestion. You've got our intelligence tech, so things like containers that are running data analysis, anomaly detection, alert notifications, hooks, that kind of thing. And then you've got all your apps, you know, and your BI systems that might be integrated with it. I'm going to focus for a few minutes on the cloud services and cloud intelligence side, because we've talked about the edge, and really no one cares about seeing a web app right now in the context of this. I mean, we have very pretty web apps. They look very lovely. We have an amazing team that design these things. And you're going to see a lot more of these from us if you visit our website in the future to see what kind of stuff we're building. But today, I'm going to focus predominantly on cloud services and the intelligence side. So telemetry ingestion. This is a very small part of our system, but it is the most crucial part of our system. And you have essentially layers. You have these protocols, HTTP, MQTT, AMQP, AMQP over WebSockets. You know, there's all sorts of new ones that come out every day. The point about this kind of these additional protocols is they all have very different characteristics. For instance, HTTP is very easy to scale linearly because it's stateless. So stick a few load balancers in place, as many devices you want, make a HTTP request, proven works really well. MQTT, really nice protocol in terms of being able to subscribe to different channels and different topics and do wildcard things. TCP/IP stream-based, so harder to scale linearly in the context of things. Same with AMQP. HTTP over carrier pigeon, I would not recommend. I mean, full stop for anything. But the point is, the point about this is that this is a section here that basically is an abstraction. You want data coming into your system like we do, and an edge telemetry ingestion system needs to make sense of it and put it into what we have is a distributed commit log. So the idea is we have one event stream for all sensor data for that instance. And that means all temperature data, all energy data, every event comes through and hits that commit log. Now, that means services can listen for messages, essentially, that they need to. But there are caveats with this, right? This is not event sourcing, by the way. It's similar in the sense that it's event-driven, but event sourcing wouldn't necessarily work here because, as far as I'm aware, and I'm not an expert in this, if you miss a, it has to be completely ordered. We're not guaranteeing ordering here. We just want a commit log of all the sensor data. So services can then stop and start as they see fit at different points in time along the commit log, which is really important if we're saying, hey, we want to stop this service, let it refill after a while. It stopped 4 hours ago. It's going to pick up where it left off and get back up to real-time speed on the time series ingestion. But what's really crucial when you're designing these types of systems at scale is that the ingestion route needs to be extremely fast. It can't have a bottleneck on databases for lookups. We've seen things just basically destroy instances of databases because its job is to just do some kind of conversion and get it onto your system as quickly as possible. Also, if you have a delay in the telemetry ingestion system, you're going to get delays in real-time data, and I'm going to touch on that shortly. Yeah, distributed commit logs themselves, like I've covered, they're extremely fast and allow us to kind of do all sorts of very clever stuff when it comes to like replaying data. And checking messages in on this commit log means that once they're there, if we have a complete service outage for a few hours and we lose data, which obviously this hasn't happened, we could replay the whole thing and get back up to where we were. Really interesting. But key points on this is the abstraction between your protocols, getting it into a straightforward like single stream, and having your services. I'm not saying we do microservices here because we don't. We have a couple of big services that, when I say big services, maybe a few medium services, that their jobs are to do one specific thing based on this telemetry stream. Really important concept to be able to scale out. So a couple of ingestion challenges. Well, I've talked about it. Devices go offline and then come back whenever they feel like it. So in consistent operation, load for a device telemetry is stable. It doesn't really fluctuate. If you've got 24/7, 365 sensor data coming in, well, it's not like a website where shopping trolleys, Black Friday, you've got consistent load across the system, and it doesn't fluctuate too much. So this is good for resource scaling, good for alerting, good for all sorts of operational things internally. But if a customer's network goes down, it's a big network. You've got thousands of devices backing up data locally every minute. You've got to get these backup payloads back in when it comes online, and that will all come in one big go. What that then presents is the challenge of getting the backup payloads in, as well as making sure the real-time data is essentially real-time, right? You don't want to have to process all the backup data, right? And then, oh, well, the real-time data is coming behind it, because if it takes 4 hours to process all the backup data, that means your real-time stream is, backed up by 4 hours. So ensuring the telemetry ingestion system can prioritize real-time data over backup data is really essential. And an example of this is recently. This is what stable load looks like on our system for one customer. Essentially, each payload, this is measuring payloads, sum of payloads over time at an interval. The top line that's flat is effectively real-time data coming into the platform, and the green line is backup data. And as you can see from that, essentially devices are coming back off and off and on all the time, right? So what's really interesting to note is with these payloads, each one of these contains on average 40 points to insert into a database. So you're seeing roughly about 10,000 readings a minute on this, maybe, and so that's roughly the equivalent of 40,000 metrics maybe a minute, right? So not huge amounts of data. So 40,000 inserts a minute, fair enough. Everything is fine in this. This is stable load. This is what happens when a customer has an outage. Basically, what happens is everything goes dead and all the devices start backing up, right? Now, fortunately, this didn't actually cause us a problem. I'm just kind of accentuating this. There wasn't actually any fires from our side, fortunately. But two things to note on this is when this in practice happens, the devices come back online. Now, the green line shows you the spike in payloads coming back in from the backup system. And what you can see is the blue line is basically, as soon as it all comes back online, it returns to normal load. That's real-time data, i.e. going through our platform and being processed, i.e. there is no latency between the backup payloads and the real-time payloads, i.e. everything comes back online, you get your real-time data, right? You also have something in the back end processing all the backup data that people may not necessarily care about. Because if you've got alerts going on, right, people are expecting text messages when things go wrong. You don't want to receive your alert that your drugs in your stability chamber have gone out of tolerance 4 hours after the regulatory compliance limit on it. That's just not good, right? So what's really interesting as well is how quick, like, notice how the graph in this case, it returns to completely normal load. The backup payloads in this instance, the graph underneath, this is the sum of the transactions for that period on our system. 0 because nothing was happening for this specific deployment, and then normal load, right? We did 87 million transactions effectively on the storage system that deals with this in that period to get it all in. But what's quite important is making sure that you can load balance in a way that means that the real-time data is not affected. Notice there was no drop in effectively latency processing this data. The line wasn't 20% under because it was having to process a lot more load. And that's basically to do with essentially making sure you can prioritize data and scale these things independently. Okay, device updates. So we just talked about, I want to update a device, say, set some logic on a device. What if it's not there, right? In an ideal world, right, devices, would be guaranteed to be online, but they're not, right? The latency of device response times when they're online can vary from seconds to minutes, so you're never going to get a guaranteed deterministic rate of return on these messages. The distributed commit log is great. It allows single streams to be read from by different services. That's really important, right? Because if I'm sending telemetry down to the device and saying, hey, tell me when you're done, it's going to come back on the edge telemetry ingestion system, right? So it's done. Really important that your backup payloads don't cause problems for, hey, please turn off the building. And you've got backup payloads coming in 4 hours later, hey, we turned off your building, but actually it happened 4 hours ago. You don't want that happening. So what's also really important is, state is ever fluctuating. You're never going to have a consistent state when you're updating devices often. So what happens is, you'll send a command down, and we use correlation identifiers for this. So every time we send something back down to the device, hey, we want you to do this, correlation identifier 1, when you're done, tell me. And that links up with something in our system that says, hey, this action was done. And that might happen 2 hours later. It might happen 3 days later, potentially. It depends. What's really important is this service, whatever's powering this, understands that the device, it has to send that data down to the device when it comes back online. That's the challenge in itself. And there are companies out there like Microsoft trying to fix that with IoT Edge. But this is essentially what happens, right? The device is offline and it waits. And again, this is a problem. It's not something you can solve. It's just something to live by. So finally, other considerations, automatically provisioning devices. It's really cool to think about, well, how are we going to provision our software automatically and everything? How is the software going to get on the device when the device comes from the factory? We had a delivery of 2,000 gateways. Oh, sorry, I've lost my iPad's about to run out. Apologies. We had a delivery of 2,000 gateways to our office. Our office basically had no lift. That means we had to spend 4 hours running up and down stairs with boxes in IKEA bags with 15 people to get them upstairs to provision them. And you might think, well, why wasn't provisioned from the factory? Well, it's quite an interesting logistical challenge to get factories from different companies to actually install software. Also, physically setting these things up, they can be different per deployment, and that can be a challenge even if you've got orchestration tools to do this. We actually built a full automation pipeline. Again, the handsome gentleman in the solar panel photo wrote a full automation pipeline on Raspberry Pis, basically, to automate the provisioning of devices. Really important. These are things we've had to do. Container orchestration is really important. You need to be able to manage the state of containers on the devices. Again, Microsoft, there are businesses like AWS trying to solve this problem. They're doing it okay. We've used it. It's interesting, to say the least, to see what kind of problems happen when you've got a lot of software engineers who have experience in designing container-based systems trying to run these things on the edge, and there are teething problems with a lot of these things right now that we're trying to come up against and solve. And then the idea of just mass provisioning and deployment that we've talked about. You can't just control F5 and test this stuff. If you're shipping out thousands of gateways, it's kind of important that, you know, there's coordination with people. And lastly, the other thing to take into consideration of, you're dealing with physical assets. Human beings make mistakes. When I say things blow up, we had a photo, this is a device, and we actually manufactured this device for a specific reason. This device was in for a couple of months. Someone went in, messed around with it, somehow managed to run, this is a low voltage system, it runs about 10 to 24 volts. Somehow it came back, oh, this is broken. Someone's clearly run 240 volts through this thing and it's gone bang. And, you know, that happens quite often, right? So you've got to be able to deal with these types of scenarios. Not only did that break that device, it broke every other device it was connected to. So it was just a chain of broken and blown up things in a panel, which again, it's funny looking back on it, but it's something that's really, really important to consider. Anyway, that is kind of a bit about Hark, a bit about the edge, a bit about the cloud and telemetry ingestion. So just as a bit of a recap, we've talked about kind of different devices, connectivity, a couple of cloud considerations when you're dealing with a lot of real-time data, and the challenges that come along with that. So I am going to flick over and try and take some questions now, and feel free to ask away. I'm surprised my internet did not go down during that. It's great. I'm not going to jinx it.
How did you convince your clients to go in and connect to? Obviously, you need to connect to the devices, and was there some sort of guarantee or insurance that you had to?
So, I mean, it's a good question. They wanted to do this. They were already looking to do this. We've been trying to do this for a couple of years. It just so happened that we had all the components to be able to do that really easily. You know, we've just talked about the challenges that we've come up against in the past. We've kind of standardized on a process now that allows us to kind of go in and do this, but it's still difficult. So you need a lot of experience in the hardware and the software and the industrial and the cloud side to make it all fit together in kind of one harmonious piece. So they were up for it, demonstrating it in small amounts, you know, so one thing, one asset, one store, that kind of thing. Really important, just so you don't want to blow something up everywhere in one go, I guess. But we've not actually, you know, I'm joking, like, you know, we blow something up. We've actually never had that kind of happen, you know, genuinely speaking. Like our team are really highly experienced. Whenever we're actually doing a controlled explosion, if I can call it that, it's usually to prove that it will blow up, because we're trying to make an assumption about something and it'll be controlled. But we've never had anything go wrong in the field like that. We just get photos of people doing it wrong in the field and, you know, looking at it and go, well, what happened there, I suppose. But yeah, it's usually the customer already interested in doing this. In terms of insurance and that kind of thing, we're actually not responsible for it. It's the installation contractor that we work with who are responsible for the electrical work. And they're the boss when it comes to that thing, right? That's really important. They are the boss. If they say electrically this isn't safe, we will not argue with them. You know, we're software people. We have a hardware heritage, but we're not gonna tell them to stick their finger on a metal plug when, you know, they think it's live, you know. Yeah, so I need to get to the chat window. How do I do this? Zoom chat, here we go, 8. Let's go. Let's see, who have we got? So Matt Ross, what is your IP stack? What is our IP stack? You mean in terms of
that box that was blank, what was in it?
Which box? There are so many boxes. Oh, the IP stack. Oh yeah, it's just like well, it's just TCP/IP. I don't need to describe how it works, because here I'm like, it's serial comms. Well, I can say, oh, this is 8 twisted pairs. You know, these are all the colors, and it does this, and frames are sent over like this. I just didn't want to go through that. Sorry. If someone wants to work on this cool stuff, where should we go? Oh, thanks, Andrew. How many sensors does the average edge device have attached to it, and do you genuinely need to tap into all of them or some of them? No, that's a really good question. So it depends on the customer requirement. So if I go back to this diagram, in the case of, you know, one device, one of these edge gateways, we've got 40 downstream devices connected to them, and each one of them has potentially 100 sensors on them. we don't necessarily collect all of them. We might collect 10 from each device and send it up, and we configure that in our platform, and we say, hey, on this device, please do this and link it up to this, and it'll just go away and make sure that happens. In certain cases, you know, you might have one asset, one big asset, one PLC with hundreds of sensors, and we might connect that up to that one single gateway, essentially. So it can depend, and it's really straightforward to programmatically control in our system. But it's not for want of, if we could get all the data, we would, but then you've got to store it, and we're generating hundreds of gigabytes of data for customers every few days. I mean, we tested something with a Cassandra cluster recently, just on test, and we ran out of space in 4 days because we forgot how much data it was putting in, and we were just like, well, this is compressed as well, shit, So it's just be mindful. We're not trying to aggregate as much data as we possibly can, because at the end of the day, someone is paying for it, usually us if the customer isn't. Sorry. I hope that answers your question, Simon. Awesome. Christoph Hayes, you packed a lot in. You're working at really impressive scale. For edge connectivity, do you use VPN connections over 4G? Really cool question. So in large deployments, it's actually a hybrid, because if you're looking at lots of locations, sometimes it might be 4G and there won't be any 4G signal. Sometimes it'll be an enterprise customer's network that we need to be connected to. So for edge connectivity, we have for certain big enterprise customers, full site-to-site VPN systems and a reference architecture for that, in order to basically go in, set up the platform in our cloud environment, and connect it with enterprise-grade VPN hardware to be able to stream all that data back and forth. In the case of 4G, we have the same capability. If everything that we do obviously is encrypted by TLS 1.2, and every device has its own independent security keys. So adding a VPN layer on top is only usually done when a customer requires it, and there's usually specific industrial requirement for that as well. I hope that answers your question, Christoph.
Any other questions?
Excellent.
Could I ask one?
Yeah, go for it.
So I'm a web developer. When I want to sort of do acceptance tests on my kit, I spin up a new instance of the website and then bombard it with user doing things to it. But you've got devices and they need things connected to them. And what's the testing around that? How do you sort of simulate a device being out in the wild? Absolutely. And connections going up and down and all those kind of things that it's got to be resilient to?
Exactly. It's a great question. The first answer to that question is simulators. So we have written quite a few simulators at our time to simulate devices, so we can test the cloud and edge connectivity piece. When it comes to physical hardware, and there are a couple of options. That device that we built, that I showed you that someone had accidentally blown up, we actually built a test jig for that. So we had and we run them through. So basically, a test jig is a piece of physical hardware that might push some buttons and do some stuff and expect an output. But it's still kind of manual to some extent. We are working on technology to automate some of this for larger deployments, like things like building control, but a lot of it is simulated. The beauty of things like PLC controllers, right, that we're working with, is that they're typically already programmed and already tested and already doing something. So as long as we can simulate a lot of that, like for instance, an energy storage system like a Tesla battery, they weren't going to send us a free Tesla battery to do integration testing on, because it cost like 300 grand, I think. I don't know. I didn't even know how, it looked really expensive, right? And when we thought about asking for one, well, our office wouldn't really fit it in any way. We would basically, it'd fall through the floor in our old converted office building. So we have to write a lot of simulators and also run a lot of controlled tests with hardware. So it's a mix, really, and we're trying to standardize as much as possible, but it's just based on experience. So to answer that, simulators, test jigs that we build, and controlled tests on the actual physical hardware in our lab, basically, that we have.
Okay, great, thank you.
Any other questions?
I suppose a chaos monkey would be the ultimate goal.
Yeah, so I mean, that would probably go down like a lead balloon, because what happens, like chaos monkey just goes and kills things, right? The last thing you want to do is go and kill something and you damage a 4,000 pound piece of equipment, which honestly, it would be, yeah, it's a fun, I don't have the budget for that, but if you're kind of you're up for it, you know, and you've got the budget, I'm fine for that.
All right. Well, if there's no more questions, thank you very much for this talk. It's very interesting. I've been waiting for a long time for this talk, and I've finally got it. So thank you very much.
There is a question. Simon Shinkins has raised a question.
Oh, hang on a second. You mentioned earlier that you're often sending control signals.
Apologies.
Hold on. You mentioned earlier that you're often sending control signals downstream in response to data received. Does that mean you have full control of these downstream systems, or control signal get interpreted by some physical system? Interesting point. Interesting conversation. The answer is depends. So we are typically in controlling things on the PLC or the building management system. So something will already be set up to prod via, you know, a comms protocol, and it will do something. To what extent of full control we have over that will depend on the architecture of the deployment. Having said this, what you saw in that photo that I showed you all the way down here is an analog control signal. So this thing's job is to take a digital I/O signal and convert it into an analog control signal. So in that case, we had to do that because there was no other way of doing it. But ideally, you know, we only do that when it's extremely cost effective to do that, you know, with large deployments. Otherwise, we are turning on registers, and the control is usually isolated to whatever registers are available to control. So that's up to whoever's programmed the PLC or whatever the manufacturer's decided. So you can change that, but typically it can be a mixture. I hope that makes sense.
Generally speaking, you try and have the safeguards in place by having the PLC layer, but if needs be, you bypass it.
Yeah, absolutely. And just on that, with control signals and safety, that's really important. So if we're controlling a building, right, we have to make sure that, you know, what happens if the gateway goes offline, what happens if the kernel, you know, panics and, you know, it's corrupt. So there are actually signals going from the gateways into the PLC to tell the PLC, hey, everything's fine, we're here, you know, we got your back, bro. And you know, if it's not there, then the PLC might say, oh crap, we better, you know, emergency this, emergency that. So that's kind of important as well. So, you know, you can't compromise safety with these things. If you're doing read-only, it's read-only. If you're doing control, you have to take safety considerations in and make sure that the PLC is programmed in a way that, you know, if your system is not there, then it will operate completely fail-safe.
Do the PLCs tend to have security limits set into them to prevent kind of things bypassing safety limits, as it were?
So yeah, that's a bit more complicated in the sense that the PLCs themselves, the program usually will be operating the safety control functions. When you're going into that PLC, you have to, there's a full industrial standard. I can't remember what it is. It's IEC 16 something or other, which basically says by default, industrial systems have to have 3 levels of access, etc. And, you know, you have to sign in with an operator control to operate and change things. When you're dealing with the control from the gateway side to that device, you can't reprogram the PLC, you know, usually. So it's limited to whatever the PLC is exposed in order to control it. But again, it can depend, you know, but ideally we're trying to make sure there's as much safety in as possible.
Thank you.
You said you had a funny story to tell at the end.
All right. Everyone's saying a funny story. Okay. So the funniest thing, I think we have a lot of funny conversations in you know, images, screenshots, things happen that you just think, how are we in this situation? In a good way. Funny story. So these inverters are made by a company called Mastervolt, and they are maybe 10 years old. And Mastervolt decided a while ago that they were never going to make inverters for buildings again. They're only going to do boat inverters for solar on boats. Well, that's great. There's some, you know, Modbus connectivity options, that kind of thing. So we download the spec to have a quick look at it. Yeah, this looks like it'll work. Plug the thing in, and nothing happens. And we're looking at the document and we're looking at the thing and going, well, if we missed something here, this just doesn't make sense. So I ring their support team in the UK and I go, hey, can I speak to someone in technical support? And they go, is it about boats or is it about solar panels? And I went, solar. And she went, oh, I'm sorry, we don't do that anymore, and put the phone down on me. So I rang back, right? about 2 minutes later, same thing, same question. Can I speak to someone in technical support? She said, "Is it about solar or is it about boats?" I said, "It's about boats." She was like, "All right, let me transfer you." Got on the phone to someone technical, and he had no idea what I was talking about. Didn't even know about the product. And so this company are owned by a company somewhere in Luxembourg or in Benelux. So I was like, right, okay, I will ring Benelux and see what they say. So I go onto the website, ring the Benelux number, and I got, I got hello, but in a different language. I'm assuming maybe Dutch or I don't know. And I was like, "Hello, do you speak English? Can I speak to someone in technical support?" And they're like, "I'm sorry, we don't do this anymore. Have you tried ringing the UK office? They should know what to do." And I was like, "Oh my goodness." So then I rang the German office number and managed to speak to someone in technical support. Again, boats, but it's Modbus, so it should be the same. It's the same bloody spec. I can see it on your site. Anyway, showed him everything. He was like, "Yes, this should work. You've wired it incorrectly. It's 2 wires only." Anyway, 2 days later, he emails back with a Word document, right? That's just like all over the place. It's not like a manual. It's just a Word document with pasted stuff in, right? And if you remember the serial comms conversation that we were having around how do we connect to them, you've got A and B, right? Plus and minus, right? On the actual physical device, it had A and B labeled, right? So we plugged it into A, plugged it into B, and wired it up all correctly. They somehow on their product had got A and B the wrong way around with the wiring, right? So no wonder they couldn't sell the bloody products. They were shipping the thing with the wrong labels on. So I'm not surprised that no one found it to work. But I mean, it took us ringing 3 or 4 different countries and 3 days talking to engineers to establish that some random person in their business had clearly found this problem and put it in a Word document, sent it to us, and just gone, "Yeah, just by the way, your A and B are the wrong way around." And we were just like, what the, like, so, wiring, electricals, humans, what can you do? So that's my story. I hope you got a good laugh out of it. So if anyone has any more questions or is interested in chatting more, then feel free to get in touch or drop us an email, drop us a tweet at Instagram, all the things. We're at Hark Sys on all of those domains, socials, things. So thanks for having me, guys. I really appreciate it.
Thank you very much.
All right.
Thank you very much. We're going to try and have Leeds Sharp next month, probably still on Zoom. And even if we come out of lockdown, I'm thinking we might have a Zoom feed in our physical location. Might get a few more people online. So thanks for turning up, and hopefully see you next month.
Yeah, nice to see everyone. Glad it
See you,
went well.
everyone. Thank you.
Bye.